Well, let's look at 45. So this is about something called a log normal distribution. The name is a little confusing. It's not the log of a normal distribution. It's a distribution whose log is a normal distribution. Say that again. Log normal, it's a little confusing, the name. It's not the log of a normal random variable, a normal distribution. Instead, it's a random variable, a distribution whose log is a normal random variable. They say x is a normal random variable and y is e to the x. So y is the exponential of a normal random variable, really. And therefore x would, which is normal, would be the log of y, ln of y. It would be the log of one of these log normals. The logarithm of y is x is going to be normal. So it's a little confusing. X is normal with mean, mu, and variance sigma squared. What are you trying to do in this problem? You're ultimately trying to derive the formula for the density, the PDF. That thing right there. And in 46, we're going to use it. So let's work on both of these problems. And essentially what the book is outlining for you is the CDF method, cumulative distribution function method. Find capital G, the CDF of capital Y first, and then differentiate it to find the PDF, the density. Let's go through those details again. So X is normal with mean, mu, and variance sigma squared. Once again, I emphasize our textbook puts the variance there, but some textbooks put the standard deviation there in that second spot. I mean, if you're doing it in the abstract, if you write it as sigma squared, it's understood to be the variance. And if you just wrote it as sigma, then it would be understood to be the standard deviation. Y is e to the x. Think about this intuitively. Pretend it's a standard normal up here. Pretend mu is 0 and sigma squared is 1. X would take on values centered at 0. And typically between -3 and 3 in such a situation. You transform those values, if you imagine those to be data values, by this formula e to the x, you're going to be taking numbers typically between -3 and 3, typically close to 0, and exponentiating. What kind of numbers are you going to get out? You could think about the graph of e to the x. And maybe go ahead and label the axes with capital random variable letters, but that's a little strange, but maybe not a big deal. If most of your data values are close to 0 and between -3 and +3, in fact, 99.7% of them, the outputs, the values of y, are going to range. In here, they're going to be positive for one thing, right? Because the output of e to the x is positive. E to the 0 is 1, so they'll be clustered pretty close to 1 mostly. Since most of these data values are close to 0, most of the outputs would be close to 1. But there would be a long right tail, e cubed. What will that be? Around 20 maybe? The scale is off. E cubed would be around 20 or something. I suppose I should do it. E cubed, yeah, I guessed right, is around 20. E to the -3, about 0.05. You could say about 99.7% of the data values will be between 0.05 and 20. Most of them will be clustered close to 1. But every once in a while, you get a high outlier. And so the distribution of y will be right skewed, positive and right skewed. The PDF of y probably looks something like this. Long right tail, PDF of y, little f sub capital Y of y. Probably looks like that. Will its peak be at 1? I would guess so. I'm not positive. We want to check that out. Because it's right skewed, the mean would be bigger than 1, actually, because of the right skew, because of every once in a while having very high outliers. I'm trying to emphasize some statistical thinking here. Data values, simulated data values, or actual data values, sometimes you're going to get pretty high values, high outliers, skewing the mean to be bigger than 1. The mean should be bigger than 1. Probably the mode is at 1, but let's just see what happens. So capital G of little y is, you could also call it capital F sub capital Y of little y. That's the CDF of capital Y. By definition, remember this is the CDF method right here. That's the probability that capital Y is less than or equal to little y. Always what the CDF is, whether the variable, random variable is discrete or continuous or mixed. Haven't done a mixed yet. We will actually, if we have time, to do a mix today. An insurance application. What do? Well, you try to relate this to x. Replace y with e to the x. You're trying to relate it to the CDF of x. I better try to isolate x on the one side of the inequality. Take the log inside the inequality. And the inequality does stay the same direction when you do so because the logarithm is an increasing function. That is the CDF of x evaluated at the natural log of y, which our book, doesn't bother with the subscript there. In this problem, they just call it capital F. And that does part A. Show G of y equals F of ln of y. Part B, differentiate it. Find the PDF. Just got to use the chain rule. Capital G prime of y equals the derivative of this function. Natural log of y is the inside function. I'm going to go ahead and keep using the subscript. Capital F sub x prime of the inside function times the derivative of the inside function. The derivative of natural log of y is 1 over y. That does part B right there, just the chain rule. You could also write this as little f sub capital X of natural log of y times 1 over y. And in fact, that helps you finish part C then, right? This is what you could call little g of y, or if you prefer, little f sub capital Y of y. I'm being inconsistent in my notation here, partially because I'm trying to use the book's notation. At the same time, I'm trying to use my notation. What do we need to finish part C? We just need the formula for the PDF of x. But x is normal. We can look up the PDF in the table. I got it marked with a sticky, but I still end up paging around to it. Right? Normal random variable, there's its PDF. Mean mu, standard deviation sigma. Just replace x with ln of y, and don't forget to divide by y. And you get the formula in the problem when you do so. This becomes 1 over square root of 2 pi times sigma times y. I'm dividing by y there. I'm trying to match the formula in the book here on the problem. Yep, okay. Times exp, which really means e to the whatever's inside the parentheses. I get 1/2, and then it's x gets replaced by natural log of y, subtract mu, divide by sigma, and square this thing. And that is the formula in the book when you square the fraction by squaring the top and the bottom. We essentially have a match. So that's the density of a log normal distribution with parameters mu and sigma, or mu and sigma squared if you prefer. However, mu and sigma squared are not the mean and the variance of y. So it's a bit confusing. They're the mean and the variance of x. They are parameters for this distribution. You see mu and sigma in the formula, but they're not the mean and the variance, or the mean and the standard deviation for y. So what would the mean and the standard deviation be? I guess we'd have to figure those out. Let's now try to use Mathematica to figure those out, and we do want to do number 46 as well, for completion's sake. Okay, so we're going to have you use Mathematica some this week. Here initially in this problem, all I'm trying to do is just get the formula for the PDF in there. I could do it this way. I could, on the palette here, which you can get to from the palette's menu, I got a writing assistant here. There is a button for a subscript right here. I'm going to do it like this. I'm going to write little g sub mu underscore comma sigma underscore of y in square brackets colon equals. I'm defining this function. It's a function of y. It's the g in the book, but it's got two parameters, mu and sigma. So I'm putting those as subscripts to give me flexibility to change those. And we'll just type in the formula in the book here. 1 over square root of 2 pi times sigma. You can make a sigma by doing escape, S escape, and a mu by doing escape, M escape. They're also in this typesetting. They're in here somewhere. You actually can do e to the, I mean, usually we do it as capital E to something. You actually can do exp as well with square brackets, representing e to whatever's in the parentheses. -1/2 times ln in Mathematica, I hope you remember, is actually log. That should do it. Enter that. What would be interesting, one thing that would be interesting is just plotting this thing as mu and sigma vary. I could do that with manipulate, right? Manipulate allows you to make animations. Plot g sub mu comma sigma, I don't use the underscores anymore, of y. Y takes on positive values here. Remember in the book, they got y positive there because y is e to the x, and e to the x can't be negative. Can't even be 0. Oh, maybe I should go up to 20 here to allow myself to capture some high outliers when x is close to 3. Start mu at 0, let it go down to -3 and up to +3. -5 to 5. Start sigma at 1, let it go down as low as 0.1 and as high as 10 maybe. That's the syntax for letting those things happen. There's what the PDF of y looks like when mu is 0 and sigma is 1. And yeah, it's got a peak close to 1. Is it exactly 1? Well, I'd have to use calculus, right? Try to maximize this function. G sub mu comma sigma prime of y. Yikes. Maybe I should try mu is 0 and sigma is 1. Simplify. Okay, that's getting better. When does that equal 0? It would equal 0 when this equals 0, which is not going to occur at y equals 1. My guess was wrong. The mode is not at 1. It would occur when log of y, ln of y equals -1. Y equals e to the -1 is where the peak is. One over e, which is about 0.37. That's the modal value. In other words, the values cluster close to 1 over e, which I was not expecting that. Okay, so that was a surprising thing to me. Mean should be bigger than 1, though, I think. We could try to find the mean just by integration. Click an integral button, go from 0 to infinity, y times g sub 0, 1 of y. Should get something bigger than 1, I'm guessing. Square root of e, yeah, that's bigger than 1. About 1.65. It's right-tailed distribution here. Can we find the mean in general for a general mu and a general sigma? I don't know if it's going to do this or not. It will require me to make assumptions about mu and sigma. Let's just see what happens. Yeah. Probably, you see, Mathematica is sometimes too fancy for its own good. It's probably assuming mu and sigma could be complex numbers, and it starts having trouble. Yeah. Okay, they're saying this is what the answer is if the real part of sigma squared is positive. So it's imagining those things are complex numbers. But it does give an answer. Is it correct? I think so. And it actually does simplify to just the numerator because this bottom essentially simplifies to 1, right? Sigma, you could think of it as being the square root of sigma squared and would cancel with that other one. So it's essentially just this for the mean. And when mu is 0 and sigma is 1, that's e to the 1/2, which is square root of e. About 1.65. Actually, Mathematica probably has a log normal distribution built in. If I go up to the help menu and go to documentation center, I bet I can look up log normal distribution. Log normal distribution is what I'm typing if you can't quite see it. Yeah, it has one. How about that? And in fact, if you did this kind of syntax with PDF in there, PDF, log normal distribution, mu and sigma, I bet we get the exact same formula that we just derived, except with an x instead of a y. There we go. That's the exact same formula that we just derived. So it's built in. It's good to see. How about doing number 46? Applying the log normal distribution. What is the log normal distribution good for? Evidently, it's good for situations like this, perhaps. Y is the diameter in millimeters of styrofoam pellets used in packing. Assume Y has a log normal distribution with those parameters. That doesn't mean the mean diameter is 0.8 and the standard deviation diameter is 0.1. These are not necessarily the mean and standard deviation of Y. In fact, they're not. They're the parameters for Y in terms of some normal distribution where the logarithm of Y is a normal distribution. Right? Log normal means the log of this distribution is normal. That's what I said. Find the probability that a randomly selected pellet has a diameter that exceeds 2.7 millimeters. So the goal here is to use this formula from 45 in Mathematica to find that probability, to have Mathematica do an integral for you. This is the PDF, this is the density. Integrating it gives probabilities. So you just got to plug in mu equals 0.8 and sigma is 0.1 into there with my G notation. And we're trying to find the probability that the diameter exceeds 2.7 millimeters. So we go 2.7 to infinity of y times G sub 0.8 comma 0.1. Now I'm sure you didn't, when you did this problem, you just hopefully typed the formula in from the textbook instead of defining a function G like I've done. So this should be the answer. It's trying to do it symbolically so you get an imaginary part, but that's effectively 0. It is meant to be 0. There's numerical error. Once again, Mathematica is being a bit too fancy for its own good. So the answer should be 0.075. Is that what you got? I thought I got something different. I tried this earlier. We want to find the probability that a randomly selected pellet has a diameter that exceeds 2.7. So this seems right. Exceeding 2.7, 2.7 or higher. I was thinking I got 0.02 or something when I did it before. Maybe I did it wrong before. Does this correspond to a certain probability for the log of y, a certain normal distribution? Would I integrate a normal distribution from 2.7 to infinity and get the same answer? We can do this. That's the PDF of a normal distribution with a mean of 0.8 and a standard deviation of 0.1. Does this give the same answer? No, it doesn't. In fact, okay, again, ignore the I part. There's the real part. That's the answer. It's microscopic. It's not the same. But there's got to be some corresponding calculation I could do to get the same answer, wouldn't there be? Anybody got a guess of instead of 2.7 here, what something different I should put there? You're on the right track. Yeah, natural log of 2.7 I think should give us the right answer. Remember, log is natural log in Mathematica. Okay, that's giving me the answer I got before. So, okay, what did I do wrong? Did it maybe my formula for G? That's correct. And I am treating sigma like the standard deviation here instead of the variance. And mu is 0.8 and sigma is 0.1 are given as the mean and standard deviation of the situation, which is not the mean and standard deviation of y. Oh, let's see. I was about to say I think I know what was wrong, but now I'm not so sure. Oh, yes, I do know what's wrong. Why am I multiplying by y? I was imagining I was doing a mean. That's better. There we go, and that matches. Yeah, the mean of y in this situation, although I'd have to start at 0, you'd want to multiply by y. The mean 2.2367, but that's not the same either, was it? Does that, oh, okay, I was thinking the more abstract situation. Does that match that when U is 0.8 and sigma is 0.1? Yeah, no.
You put 8 instead of 0.8.
Okay, thank you. There we go. Okay, that matches. This is the mean in general for a log normal distribution with parameters mu and sigma. And that's going to get pretty big pretty fast as either mu or sigma increase. Coming back to the picture of the PDF, how does changing mu and sigma affect things? The density definitely moves to the right as mu and sigma increase pretty rapidly, especially as sigma rapid. Thinking did that. Wild. Oh, kind of unexpected things going on here. As sigma increases, the mean should increase as well. So that's a bit confusing. Seems like the mean is decreasing. I'm not sure what's going on there. So more mystery that I'll have to investigate because I'm not quite sure what's going on. As far as part B goes, you have to probably do a little experimentation, or, well, you know the 68, 99, 95, 99.7 rule for normals. About 95% are going to be within 2 standard deviations of the mean. For the corresponding normal random variable, the ln of y is a normal with mean 0.8 and standard deviation 0.1. And about 95% will be between 0.6 and 1.0, right? Within 2 standard deviations of the mean. So to find the corresponding values of y, just exponentiate those. The answer should be, for part B, should be e to the point, between e to the 0.6 and e to the first. And e to the first is, of course, e. So should have gotten about 1.82 and 2.72 for part B. Let's confirm it by integrating. So if I go from 1.82 here to 2.72, should be close to 0.95. Yeah. So he's using the 68, 95, 99.7 rule that for a normal distribution, about 95% of the values are within 2 standard deviations of the mean. For not y itself, but the natural log of y, which will be normal with that mean and that standard deviation. To say for that variable, about 95% will be within between 0.6 and 1 within 2 standard deviations of the mean. And then exponentiating those is going to get the corresponding values for y. Y equals e to the x, right? Exponentiate. So I imagine that probably felt difficult for most of you to figure out exactly what was going on there. But I hope this exploration cleared it up some. Can we do simulations in math? Like, yes, you can. The key, I showed you a notebook where I had a random choice in there, but really in general, the key command is RandomVariate. RandomVariate. Very flexible command for doing lots of probability simulations in Mathematica. This will do a random variable, a simulated random value from a normal distribution, that's standard normal, in fact, when you don't have anything inside there, the assumption is it's standard normal. So you enter this over and over again, about 95% of the time, for example, you're going to get between -2 and 2 within 2 standard deviations of the mean. In fact, maybe we should do comma 100 here. Now, about 68% of those between -2 and 2, we could, how do we do this? Count. I forget how count works. You know what? I forget how things work in Mathematica myself, so I always just have to look things up and mimic other examples. Count can count the number of things in a list with a pattern. That looks confusing. Those examples look confusing. I know I've used it before. Maybe count if. No, okay. I know I've used count before in this kind of way, unless it was a slightly different command. So I'm a little confused about these examples. I could count how many things are between -2 and 2 in this list. And it should be about 95% of them, right? Did I say 68% before? About 68% would be between -1 and 1, right? About 95% would be between -2 and 2. We should only see about 5 that are not between -2 and 2. That's probably a better way to look at it. See any 2s or -2s? There's one. There's another one.
There's another one right to the left of the one that you just found.
Right there. There's a third. Probably we might find 1 or 2 or 3 more. I'm not seeing any more at the moment. Confirming the 95% or so that are between -2 and 2, and so about 5% or slightly less between either bigger than 2 or less than -2. If we mimic this, evidently we can simulate from log normal. Maybe I should do this. Maybe I should, let's go X data, random variate, normal distribution, thinking about problems 45 and 46, with mean 0.8 and standard deviation 0.1. Let's do 100 simulated values there. From a normal distribution with a mean of 0.8 and a standard deviation of 0.1. So these numbers are all close to 0.8. Could I transform these values, y data, using the exponential function e to the x to get a log normal situation? Yeah, you can. How? I think I can just do this. X data. I think I can do that. These are now log, this is now log normal data. I'm applying the exponential function to all those numbers that were in X data. The mean of the numbers in X data, and you can use mean of X data, that should be close to 0.8. Mean of Y data should be close to e to the 0.8. Close to 2.2, a little less. Yeah, a little less than this. Is it matching? Is the data matching the graph of the PDF for this log normal distribution with parameters 0.8 and 0.1? Very skinny and tall. Clustered close to e to the 0.8, which is 2.2. So maybe I should just go from 1 to 3 here or so. Well, let's start at 0. if I made a histogram statistics of the Y data, would it match this? It should. I don't know if it would make sense to plot them on the same scale or not, same axes here. I'm not sure if this is going to work. Okay, it sort of works. I think I'd like more bars in the histogram at least. Histogram. How do you make more bars? Options. It's not so clear here. Chart. Maybe I just need to look for more examples or something. Look into this. Trying to add more bars to the histogram. You'd think it'd be easier to find an example of this. None of those look like they would help. Okay, I'm not going to worry about it then. Okay, reasonable. But these match. Actually, the PDF for this log normal for this example doesn't look too much different from a normal, does it? It's pretty symmetric, this curve down here. You could probably approximate it with the normal, but the mean would be close to 2.2 instead of 0.8. And yeah, you could use random variate also to simulate from a log normal distribution. And this is going to produce different simulated data. But if I made a histogram of the Y data and the new Y data, they're probably not too different looking. Just trying to put two histograms side by side here. Same general pattern, centered close to 2.2, with roughly the same amount of spread. So you can use random variate in lots of ways. I don't know if I'll have time today, but for sure on Thursday, I'll show you another way to use random variate for simulation for user-defined distributions. You know, normal distributions, log normal distributions, exponential distributions, gamma distributions, chi-squared distributions, those are all well-known distributions. But what if you're in a real-life situation where you've got to, none of those distributions seems to be a good fit for your data? Maybe you've got to come up with an entirely new distribution on your own that seems to work better. Does that ever happen? Maybe. I'd say most people use well-known distributions, but theoretically it could come up. So I'll show you for sure on Thursday, maybe today, that you can come up with user-defined distributions.